Before we get into a deep dive on the behavior of contemporary neural language models on grammatically interesting and potentially revealing setups, I want to say a few more words about the notion of explainability of computational models and of AI systems. So let's take the domain of computer vision as an analogy. So an ideal explainable state-of-the-art AI system can not only do what we're picturing here. So what we're picturing here is that there's an input that is, in this case, a picture of a cat. The artificial system takes it in, does some processing of that input, and processes it into a form that can be then interpreted as, this is an instance of the category cat. So there's some set of categorizations that are possible, and that categorization is an output. Right now, that's all that a current model can do. So what can I explain about the input and about the output? Nothing. Simply, this is a cat. That basically is no more and no less than the output of the system itself. But if you ask a human the same thing, you say, like, first of all, I ask the human, what is that? And I would say, well, that's a cat. But I can also go farther. If you ask, how do you know that that's a cat? Why do you say that that is a cat? I, as a human, can do much more. I can tell you, well, I noticed features of it that are cat features. So, for example, it has fur. It has whiskers. It has claws. It has the feature of these pointy ears, which distinguish it from other things that have fur, whiskers, and claws, like rats, for example. It has a different kind of ear than a rat. It is a different size than a rat. It has different facial structure than a rat, and so forth. And so these are features that I can then resort to and say why I made that decision. And I may not be perfect in my introspective analysis of my own decision, but I can still give reasonable justifications. State-of-the-art AI systems, you saw that unlike n-gram models, unlike PCFGs, the individual components are not in a contemporary recurrent neural architecture things that we can interpret directly in terms of linguistic units. Nevertheless, they perform really, really well. And this presents a challenge for explainability. And in the applied setting, that explainability challenge is actually something that is potentially a real concern, because it's difficult to make an unexplainable system accountable. So for a variety of kinds of applications, for example, for medical decision-making, where I might want to take a patient's medical record and use an AI system to make recommendations to a doctor, or it's a self-driving car that's deciding how to behave in a potential hazard situation, or it's even an automated personnel decision, like an NLP model that is deciding what to do with the resumes that job applicants have. If I have a system that gives me outputs, but I don't know why it's giving me the outputs that it does, for any of these cases and more, then it's a problem for the deployment in our contemporary society. Another reason for wanting something that's explainable, or more broadly, to understand more deeply the behavior of the artificial systems that we're developing, is that explanation is actually like a fundamentally human part of our behavior. So this is a scene that I think will resonate with everybody here, and there are lots of reasons. We ask very naturally, what is the reason for which the child behaved in the way that we're seeing, pushing over a tower? And if I could ask the child, and even a child of only a few years old will readily give an explanation. What are the explanations that the child might give in this situation? For example, well, knocking over a tower is the best part of building it. That might be one thing that child says. Or, I was jealous of my brother. Perhaps it was the brother that constructed the tower. Or, the tower was in the way of the TV set. These are all fundamentally different motivations that might give rise to the same behavior. So the surface behavior in an uncontrolled setting is not really enough information for us to really understand the system, and we have to probe more deeply. And there are a couple of different ways we might probe more deeply. But to bring it back to contemporary neural language models, remember that the state of the art for language models tends to look something like this. It is a system of continuous vectors that are updated with a complex variety of rules according to a set of weights that are implicated in computations in the system in a number of points in a distributed fashion. But because of this distribution, unlike n-gram models and grammar-based models, the way that this knowledge actually influences computation is opaque without further inspection, without further interrogation. And so there are a variety of ways that we can try to understand and explain the behavior of a model like this. And two of them are one, controlled testing, so setting up minimally differing controlled settings to try to understand the behavior of a model and see how systematic changes to its inputs systematically change its outputs. And the other is to actually probe the internals of the circuitry underlying the behaviors. And for the rest of today and for the next lecture, we're going to be using these kinds of methods to try to understand more deeply the abilities and the limitations of contemporary models. We're mostly going to be using controlled tests, but I'll also refer a little bit to ongoing work that tries to probe the circuitry a little bit. So we'll stop for a moment, take a break, and then come back to dive into our first example of a controlled test.